Hello again. This is our second lesson on work and energy. We know that they are very closely related to each other. We know that energy gives something the ability to do work. That could be your food energy or the potential energy of a raised brick or the kinetic energy of a moving spacecraft or a meteor. And work is what changes the energy of an object. So by doing work to, say, lift a sledgehammer into the air, maybe that's you give that sledgehammer the ability to do work when it is lowered onto something. By the way, I've never hammered a sledge. I don't really know why it's called a sledgehammer. Maybe you could look that up. The net work on an object is going to be the total force. That's what that little summation symbol means right there. The sum of all the forces times the distance, and here of course we're assuming that those two vectors are parallel to each other, so we're dropping the whole cosine of theta thing for the time being. If they are parallel, it's the sum of the forces times the distance. That's why it's called the net work, because it's the work done by the net force. But net force, as you all know from Newton's second law, is mass times acceleration, and so it looks like net work is mad, but it's actually just mass times acceleration times displacement. Now, from our old kinematics formulas, we know that displacement can be represented in several other ways. For example, final velocity squared minus initial velocity squared over 2 times acceleration. That came from the old formula that you might remember, 2 times acceleration times displacement equals final velocity squared minus initial velocity squared. That look familiar? If not, go back and review the kinematics lessons. But that means we can replace the displacement with this. And of course, if we do some distribution and some cancellation, we end up with this, that we get 1/2 mass times final velocity squared minus 1/2 mass times initial velocity squared. Notice that the accelerations in fact cancel out. What does this mean? Well, since we know that work causes changes to the energy of an object, that means if we can define kinetic energy, the energy associated with motion, with a mathematical formula of 1/2 mass times velocity squared, then that means if we go back to that previous slide, we have that the net work is equal to the change in kinetic energy, final kinetic energy minus initial kinetic energy. Note the unit here. Kinetic energy would be 1/2, let's see, mass is kilograms, velocity is meters per second, so velocity squared is meters squared over second squared, and sure enough, that is in fact a joule. That's the same thing that you would get when you multiply a Newton times a meter. A Newton is a kilogram meter per second squared, and then times another meter gives us this. So once again, energy is shown to be in joules in the SI system, other units in other systems. So the question becomes, of course, can kinetic energy ever be negative? Well, mathematically, it's pretty clear that it can't. The mass is never negative, and the velocity is never negative. And so, well, actually, velocity can be negative. It all depends on the positive direction, but we are, in fact, squaring it. So once you square it, it's never negative. So kinetic energy can never be negative mathematically. Commonsensically, it also can never be negative, because the slowest an object can move is to not move, right? And when it's not moving, its kinetic energy is 0. It can't go any slower than that. And so it cannot have negative kinetic energy. Potential energy can be negative because it depends on where you set 0 potential energy at. Is it at the surface of the Earth or at the top of the Empire State Building? So that leads us to the work-kinetic energy theorem, and believe it or not, we've already demonstrated it. And that is that the net work done on an object is equal to its change in kinetic energy. Notice something important here. I said net work, and it's equal to the change in kinetic energy. If there's no change in kinetic energy, then that must mean that the object is not changing speed. And if it's not changing speed, then that means there's no net work being done on it, because there's no net force on it, at least not in the direction that it's moving. And so we get that the net work is the change in kinetic energy. Notice, by the way, that I said a few minutes ago that kinetic energy can never be negative, But changes in kinetic energy can be negative. It all depends on how you relate the final kinetic energy to the initial kinetic energy, whether it gains or loses. So if the speed of an object increases, for example, the change in kinetic energy is greater than 0 because the final kinetic energy is bigger than the initial kinetic energy. It's moving faster. On the other hand, if the speed decreases, then the change in kinetic energy is negative because the final kinetic energy is smaller than the initial kinetic energy. Neither one of them is ever negative, but the change can be. All right? With that in mind, I think we can go straight to an example. Our example involves the movement of a car. A 1,000 kilogram car accelerated from 25 kilometers per hour, that's its initial speed, with a net force of 4,000 newtons as it moves 500 meters. Now, where does that force come in? Well, that's the force with which the tires push backward on the road with friction. But that means by Newton's third law that the road pushes forward with a force of 4,000 newtons on the tires, and that's what makes the car move. Isn't that weird? It's the road pushing the car forward. We're going to answer 3 questions based on this information. We're going to find the change in the kinetic energy of the car. We're going to find the final kinetic energy of the car, and we're going to find the final speed of the car. Now, I can tell you right now, you could have used other methods to find the final speed, but we're going to use this method, and we're going to find these things in precisely this order. And there's a point to that. You'll see that coming up. So what do we do first? Well, of course, we list our variables. I've done them all for you right there. Note that the initial velocity I converted from kilometers per hour to meters per second. We need to do that because we're in SI units here, newtons and joules and stuff like that. So that had to be changed. If you've forgotten how, just remember that there are 1,000 meters in a kilometer and 3,600 seconds in an hour. Let's work our way through each part of the problem. Part A, the change in kinetic energy. Well, the thing to remember is what we just learned. We had a formula that said that the net work is equal to the change in kinetic energy. Well, the net work is just the net force, which is 4,000 newtons, times the displacement, which is 500 meters. Note that the road is pushing the car forward, so it is parallel. We don't have to worry about cosine of theta. And so our answer is going to be, well, we got 20, and then we've got 5 more zeros. And it looks like the answer is going to be 2 million joules. Okay? So that's as easy as that was. That is the change in kinetic energy. See, what you were probably thinking is, well, change means final minus initial. So if we can find the final kinetic energy minus the initial kinetic energy, we can get the answer. That's true. But in this case, since we have the Work-Kinetic Energy Theorem, wasn't that a whole lot easier? Always remember, an equation has 2 sides, and you're welcome to use both of them. So let's move on to part B. Let's find the final kinetic energy. Well, the thing to remember about this is change means final minus initial. So that means that the final kinetic energy is equal to the initial kinetic energy plus the change in kinetic energy. Since we already know the change in kinetic energy, we found that up here in part A, we need to find the initial kinetic energy, and then it just becomes an addition problem. Well, the thing to remember here is that kinetic energy is, of course, 1/2 mass times velocity or times speed squared. So this is going to be 1/2 times the mass, which is 1,000, times the speed, 6.94. By the way, that was rounded. It's actually 6.9 with the 4 repeating, so I can toss a couple more 4s on there. Don't forget to square that. Put the numbers into your calculator and see what you get. My calculator says that the answer is about 24,100 joules. And so that means that the final kinetic energy is, well, you add those two together, the initial and the change, and you get 2,024,100 joules. Now that's 5 significant figures, which is way too much precision for a problem like this. We're talking about a car. That would imply that we know the mass to 5 significant figures. That's impossible. But it does help us with the next part of the problem. So we go to part C to find the final speed. And as I mentioned, there are other ways of doing this, but I think you're going to like this. You see, since the final kinetic energy is equal to 1/2 mass times the final velocity squared, I can just plug those into the formula for kinetic energy. So we have 2,024,100 equals 1/2 times the mass, which is 1,000, times the final speed squared. Now pop them into your calculator and see what you get. I don't know about you, but I happen to get that the final speed is about 63.6. Let's round that to 64 meters per second, which, by the way, is really fast. That's about 200 feet per second, so that would be 150 miles an hour, something like that. I'm not sure. All I know is it's quick, and it did it in only 1/2 kilometer. So that's pretty impressive acceleration. But then again, I just made these numbers up. So that's how you work kinetic energy problems. No pun intended there. We did work. We related it to change in kinetic energy, and we were able to use that to solve a problem, ultimately to find a speed. That's how you work them. Practice these, and you'll get really good at it. Thanks. Bye-bye.